Welcome back to Complicated Stuff, everybody. I'm Thomas,
And I'm Jenna.
and we are both part of the Girl Has It All team.
That's right.
Glad to have you all back for our 16th episode.
It's great to be back.
And today we are going to be exploring a topic
Yeah.
that is just about as mind-boggling as the quantum realm,
Oh, absolutely.
but maybe on a much larger scale.
Yeah.
We're talking about the Earth's deep mantle.
Okay.
So imagine a world beneath our feet with intense heat,
Right.
crushing pressure,
Crushing pressure.
and structures so enormous they dwarf entire continents.
It's a place that we've only really started to learn about relatively recently.
Yeah.
But new research is really starting to shed light on what's down there.
What is one of the biggest surprises that scientists are uncovering about the deep mantle?
Well, one of the most fascinating discoveries has been the existence of these massive zones called large low-shear-velocity provinces, or LLSVPs.
Okay.
They're located right on the boundary between the Earth's core and the mantle, and they're truly colossal. Think continent-sized blobs sitting beneath Africa and the Pacific Ocean.
Continent-sized blobs.
Yeah.
Deep beneath our feet.
Deep beneath our feet.
That's crazy.
Yeah, it's pretty wild.
So what makes these blobs
Yeah.
so different from the rest of the mantle?
Well, they're called low-shear-velocity provinces because seismic waves, so those vibrations that travel through the Earth, actually slow down when they pass through these zones.
Really?
It's like they're hitting a speed bump in the Earth's interior. And that slowing down tells us that the LLSVPs are different from the surrounding mantle.
Okay.
They're either denser or made of different stuff altogether.
Okay, so we've got these massive, mysterious zones
Yes.
in the Earth's deep mantle.
Right.
What are some of the theories
Yeah.
that scientists have about where they came from and what they're made of?
Well, there are two main schools of thought.
Okay.
One theory is that LSVPs are basically graveyards of ancient oceanic crust. Over millions of years, oceanic crust gets dragged down into the mantle through a process called subduction.
Right.
This crust is denser than the surrounding mantle rock, so it sinks down to the core mantle boundary and piles up, forming these LLSVPs.
So it's kind of like a geological recycling bin at the bottom of the Earth.
Exactly.
Okay, cool.
The other theory, which is just as intriguing, proposes that LLSVPs are remnants from the very early Earth,
Okay.
made up of primordial material that's been down there since the planet's formation.
Wow.
This material would be chemically different from the rest of the mantle,
Right.
and it could hold clues to the conditions that existed billions of years ago.
So how do scientists figure out which theory is more likely? I mean, we can't just dig down there and take samples.
Right, that's the challenge.
Yeah.
But luckily, we have natural laboratories on Earth's surface that can provide some clues.
Really?
Volcanoes,
Volcanoes.
specifically volcanoes that sit right above the edges of these LLSVPs.
Okay, so how can studying volcanoes tell us about something that's buried thousands of kilometers below the surface?
Well, the magma that fuels these volcanoes rises from the deep mantle, bringing with it chemical traces of the material it passed through on its journey to the surface.
Right.
It's like a message in a bottle, except the bottle is molten rock.
That is a very dramatic message.
It is a dramatic message.
So which volcanoes are scientists looking at to study these LLSVPs?
Well, one of the most fascinating natural laboratories for this kind of research is the Galapagos Islands.
The Galapagos Islands.
Yeah,
Yeah.
these volcanic islands sit right above the edge of the Pacific LLSVP,
Okay.
making them a prime location to study how the deep mantle influences surface volcanism.
So what have scientists learned from studying the Galapagos volcanoes?
Right.
Is there anything unique about their composition
Yeah.
that points to the origin of the Pacific LLSVP?
Well, what's interesting is that the Galapagos Islands display what we call bilateral asymmetry.
Bilateral asymmetry?
Uh-huh. The western and southern islands, which are closer to the LLSVP, have lava with a distinct chemical signature,
Okay.
different from the lava found in the northeastern islands.
So what is this difference in the lava?
Right.
Tell us about what's going on beneath the surface.
Well, it suggests that as the material from the LLSVP rises to fuel the volcanoes, it's mixing with regular mantle material from other parts of the mantle.
Okay.
Imagine swirling together two different colors of paint.
Yeah.
That's kind of what's happening beneath the Galapagos.
So to decipher the message these volcanoes are sending us, we need to analyze the composition of that mixed paint.
Exactly.
How do we go about doing that?
Well, that's where we need to get down to the mineral level.
Okay.
And there's one mineral in particular that acts as a sort of geochemical fingerprint.
Uh-huh.
Olivine.
Olivine.
It's a very common mineral in volcanic rocks.
Okay.
And the chemical makeup of olivine crystals can tell us a lot about the origins of the magma they formed in.
So these tiny olivine crystals are like detectives holding clues about the deep Earth.
That's a great way to put it.
What kind of information can they reveal?
Well, scientists are particularly interested in looking for signs of a type of rock called pyroxenite within the olivine.
Pyroxenite.
Pyroxenite is thought to form primarily from recycled oceanic crust.
Okay.
If scientists find a lot of pyroxenite in the Galapagos lavas, it would support the idea that the Pacific LLSVP is indeed a massive pile of old crust.
Did they
Find that?
That's where things take an unexpected turn.
Okay.
They did find evidence of pyroxenite, but not where they expected it. It was most prominent in the north central islands,
Right.
not the southwestern islands closest to the LLSVP.
So what does that mean for our understanding of the Pacific LLSVP?
Well, it throws a wrench into the simple piles of crust idea.
Okay.
It suggests that the LLSVP itself may not be dominated by recycled oceanic crust after all.
So if the LLSVP isn't just a pile of crust,
Right.
what else could it be?
Does this new evidence lend support to the idea that it might be made of primordial material?
It definitely makes that theory more intriguing.
Okay.
We also see evidence of this in the unique helium isotope signature found in some Galapagos lavas.
Okay.
This particular signature points to an incredibly ancient source, something that's been isolated from the rest of the mantle for billions of years.
Wow. So instead of a straightforward pile of crust, the edge of the Pacific LLSVP seems to be much more complex than we initially thought.
Yeah, it's definitely more complex.
What kind of picture is this new research painting?
Instead of a homogeneous mass picture, the edge of the LLSVP as a dynamic and heterogeneous zone, almost like a mosaic.
Go ahead.
We have this potentially primordial material as the base with ancient slabs of oceanic crust, the pyroxenite, embedded within it.
So as the LLSVP material wells up to feed the Galapagos volcanoes, it interacts with these pockets of pyroxenite,
Exactly.
creating that mixed paint signature we see in the North Central Islands.
Precisely, and this research really challenges our understanding of the deep mantle. It's not just a simple layering of different materials,
Bro.
but a dynamic system with complex interactions happening on a massive scale.
This is blowing my mind.
I know, it's pretty wild.
We had these giant blobs beneath our feet,
Yeah.
possibly leftovers from the Earth's earliest days with chunks of ancient ocean floor mixed in.
Yeah,
It sounds like something straight out of science fiction.
it really does.
So what are some of the broader implications of this research?
Well, it suggests that the LLSVPs, these massive structures that influence plate tectonics, volcanism, and even the Earth's magnetic field, might be remnants of the Earth's earliest history.
Okay.
And that has profound implications for our understanding of how our planet formed and how its interior has evolved over billions of years.
It sounds like we're just beginning to scratch the surface of what these LLSVPs can tell us about our planet.
Yeah, absolutely. There's so much more to learn.
But before we dive deeper into those implications, let's take a moment to hear from you. What are your initial thoughts on these massive structures lurking beneath our feet? Do you find the idea of primordial material as fascinating as we do?
Let us know.
Let us know. We'll be back after a short break to discuss what else we can learn from these enigmatic LLSVPs and what their existence might mean for the future of our planet.
These enormous LLSVPs, potentially holding secrets from the Earth's infancy, are influencing our planet in ways we're only just beginning to understand.
Yeah, it really puts things into perspective.
Yeah.
We walk around on the surface, going about our daily lives, and meanwhile these massive ancient structures are lurking deep beneath us, shaping the very world we inhabit. What else can we learn from these LSVPs?
Oh,
What kind of impact do they have on the processes happening under Earth's surface?
one area where LLSVPs might play a significant role is in volcanism. We already touched upon how the Pacific LLSVP seems to be influencing the chemistry of the Galapagos volcanoes. But it goes beyond that. Many of the Earth's hotspots, those areas of intense volcanic activity, are located right above the edges of LLSVPs.
So these LLSVPs are like the hidden powerhouses driving volcanic activity around the world.
That's a great way to put it. They're not the sole cause. Of course, volcanism is a complex process with multiple factors at play.
Right.
But the presence of these large, hot, and potentially chemically distinct masses in the deep mantle can certainly influence where and how magma rises to the surface.
It makes you wonder if understanding these LLSVPs better could help us predict volcanic eruptions more accurately.
Absolutely.
Volcanoes are incredibly powerful forces of nature.
Yeah.
And being able to anticipate their behavior could have a huge impact on people living in volcanic regions.
If we can gain a better understanding of how LLSVPs interact with the surrounding mantle and how that influences the movement of magma, it could lead to more accurate predictions of volcanic eruptions. This kind of knowledge could save lives and help communities prepare for potential volcanic hazards.
Yeah, it's amazing to think that these deep-seated structures, thousands of kilometers beneath our feet, could have such a direct impact on our lives.
It really highlights the interconnectedness of our planet. Everything is linked from the core to the crust, and it underscores the importance of continuing to study these hidden realms. The more we learn about the deep Earth, the more we understand about the processes that shape our world.
It's like solving a giant planetary jigsaw puzzle. Each new discovery adds another piece, bringing us closer to a complete picture of how our planet works. But speaking of puzzles, the composition of these LLSVPs is still a bit of a mystery, isn't it?
Yeah.
We've talked about the possibility of them being made of primordial material.
Right.
But is there any other evidence to support that idea?
There are a few other intriguing clues. Aside from the helium isotope signature we mentioned earlier, scientists have also observed some unusual characteristics in the seismic waves that pass through LLSVPs.
Okay.
These waves suggest that LLSVPs might be slightly less viscous than the surrounding mantle.
Less viscous. What does that mean exactly?
It means they might be slightly more gooey or flow more easily. Now, this difference is subtle, but it's significant because it hints that the material within LLSVPs might have a different composition or thermal structure than the rest of the mantle. This finding adds another layer of complexity to the puzzle.
So if LLSVPs are indeed less viscous, what could that tell us about their origin or behavior?
Well, could mean that they're more easily deformed by the forces within the Earth's mantle. Imagine pushing your hand through honey versus pushing it through a thick dough. The honey being less viscous will deform more easily.
Okay, so the less viscous nature of LLSVPs could influence how they interact with the surrounding mantle and how they respond to the Earth's internal heat. Could this also play a role in their potential connection to plate tectonics?
That's an area of active research. Plate tectonics, the movement of the Earth's massive crustal plates, is driven by the heat churning within the mantle. Some scientists believe that the presence of these large, potentially less viscous LLSVPs could influence the patterns of mantle convection, the process by which heat is transferred within the Earth.
So these LLSVPs might be more than just passive blobs sitting at the bottom of the mantle.
Yeah.
They could be actively influencing the movement of plates above them, shaping the very continents we live on.
That's a possibility that's both exciting and a bit daunting, isn't it? These massive structures hidden deep beneath our feet could be exerting a subtle but powerful influence on the Earth's surface, shaping our planet over millions of years.
It's mind-blowing to consider the scale and interconnectedness of these processes.
Yeah.
It seems like every new discovery about LLSVPs raises even more questions. What are some of the most pressing questions scientists are hoping to answer through future research?
One of the biggest remaining mysteries is their precise composition.
No.
While we have some clues from seismic data and volcanic samples, we still don't have a definitive answer to what these LLSVPs are actually made of. Are they truly remnants of the early Earth preserving a record of our planet's formation? Or are they the result of a more complex interplay of processes throughout Earth's history?
Those are some big questions. How are scientists hoping to get those answers?
Well, continued seismic studies will be crucial. By analyzing seismic waves in even greater detail, we can create more refined images of the Earth's interior, giving us a clearer picture of the structure and composition of LLSVPs.
So it's like using sound waves to see inside the Earth.
Exactly. And there are also ongoing efforts to develop techniques for actually sampling material from the deep mantle. This is incredibly challenging, of course, given the extreme depths and conditions involved. But if we can obtain even a tiny sample of material from an LLSVP, it would be a scientific treasure trove, providing unprecedented insights into the Earth's interior.
It sounds like we're on the cusp of some truly groundbreaking discoveries about our planet.
I think so.
What other areas of Earth science do you think will be most impacted by what we learn about LLSVPs in the coming years?
Well, understanding LLSVPs will have far-reaching implications for our understanding of plate tectonics, volcanism, and even the Earth's magnetic field. It could also shed light on the evolution of other rocky planets in our solar system.
This is all incredibly fascinating, and it makes me wonder what our listeners think. Are you as captivated by these mysterious LLSVPs as we are? What questions do you have about these massive structures lurking beneath our feet? We'd love to hear your thoughts. Share your comments on social media using the hashtag #ComplicatedStuff. But before you do, let's wrap up our exploration of these enigmatic LLSVPs. We've only just begun to unravel the mysteries surrounding these LLSVPs, but even with what we know now, it's clear that they have profound implications for our understanding of Earth's past, present, and future.
Yeah, it really is remarkable how these remnants of Earth's deep history aren't just these inert blobs sitting passively in the mantle. They're dynamic entities, interacting with the surrounding mantle, influencing plate tectonics, driving volcanic activity, and perhaps even playing a role in shaping the Earth's magnetic field.
So incredible to think that these structures so deep and hidden from view can have such far-reaching effects on the world that we experience every day.
It really is.
What aspects of Earth's future do you think will be most influenced by what we continue to learn about LLSVPs?
Well, understanding the dynamics of LLSVPs could be crucial for predicting long-term geological processes. For instance, we know that the Earth's continents have shifted dramatically over millions of years. Could LLSVPs influence the future movements of those continents?
That's a great question. Could they cause new continents to form or even cause existing ones to collide?
It's certainly possible. As we delve deeper into how LLSVPs interact with the mantle and influence plate tectonics, we may be able to model these processes and gain insights into the future configuration of Earth's continents. Imagine being able to predict the formation of new mountain ranges or the opening of new ocean basins millions of years from now.
Wow, that would be revolutionary. It would change our entire understanding of geological timescales and the forces that shape our planet.
It really would.
Beyond the grand movements of continents, could understanding LLSVPs help us better understand the future of volcanic activity on Earth?
Absolutely. As we mentioned earlier, many of Earth's hotspots are located right above the edges of LLSVPs. By studying the interaction between LLSVPs and the surrounding mantle, we might be able to better predict the locations and intensities of future volcanic eruptions.
So this knowledge could be invaluable for mitigating volcanic risks and protecting communities in volcanic regions.
For sure.
It's amazing how something so seemingly distant and obscure can have such a direct impact on human lives.
It really highlights the interconnectedness of our planet and the importance of understanding these fundamental Earth processes, and it emphasizes the power of scientific inquiry. By asking questions, gathering data, and testing hypotheses, we can unlock the secrets of our world, even those hidden deep beneath the surface.
This has been an incredibly enlightening journey into the depths of the Earth. It's left me with a newfound appreciation for the complexity and dynamism of our planet.
Me too, and it's a reminder that we're still just scratching the surface. There's so much more to discover about the Earth's interior, and each new discovery has the potential to reshape our understanding of our world.
Well, on that note, we want to hear from you, our listeners. What are your thoughts on these enigmatic LLSVPs? What questions do you have about these massive structures lurking beneath our feet? Join the conversation on social media using the hashtag #ComplicatedStuff. And remember, keep those brains buzzing. Until next time on Complicated Stuff, keep exploring the world around you from the familiar surface to the uncharted depths below.